So this is the last JAC of the season, the last seminar of the season. And so Professor Bhuvnesh Jain is visiting us from Penn, Philadelphia. And it's personally, for me, an honor to have Bhuvnesh here in Bologna. So I met him a long time in 2006 when I was a grad student in Padua, and I spent 6 months in Philadelphia, and it was absolutely a fantastic experience in the University of Pennsylvania. So Bhuvnesh got his PhD at MIT. Co-supervisor Berchinger and Woods, and he was postdoc at MPI in Munich. So he was postdoc at MPI in Munich, where he met many distinguished scientists that you know, and I met during my career, like Battiferro and Antonio Battiferro. Ravi was there, Piero Rosati was there in the same period. And then he moved to US, Johns Hopkins University, and
Carlo, we're getting a lot of echo.
No, okay, yeah.
So
I was co-director of the. On photometric survey, is involving LSST and Euclid. Technical problem, but we are there. Are people online able to listen?
I think it's better now.
Okay, great. Thanks, Ben.
which one is
The keynote, this one. Keynote, I think that's
No.
no.
Where is the?
Excuse me.
Please share the which one?
Oh, perfect. You can share the text.
Yes.
I can share the text. Perfect. Yeah.
You can share the desktop and then go in presentation mode for it.
Right. And no, it's great. Now it's working. Now you can play, and that's it. Yeah, perfect. Play, and Enrico play. Okay, perfect. Great. Okay, thank you. So Bhuv is going to talk about exploring the cosmic puzzles with gravitational lensing, and is. Thank you, Enrico. Thank you. So let me. Okay, great.
Thank you very much. Carlo is exactly the same since 2006. It's great to be here. I've had a really nice, productive visit, and glad to see you all. How many are cosmologists in this audience? Half. And students? I mean, I can guess by the. Okay, great. Please feel free to ask questions in between. I'm aiming for 50 minutes.
Yeah, 45.
I don't usually share full screen. The slides on.
No, yeah.
Okay.
Yeah, okay, click on astrophysics there. Click here, then try to make it larger. See, so you're already sharing, right?
No, I stopped sharing, so I can
Okay.
start again. Okay.
Right? Continue to share.
Okay, great. All right. Sorry about that. So I'll try to explain why in cosmology there are two things happening which make this kind of a transition point. One is that in our methodology, we have hit a lot of bottlenecks. And so we are switching how we do cosmology, how we test theory and data. For example, a lot of machine learning. And then the results are extremely confusing. So this is a great time either to enter cosmology or get the hell out of it. Mike, I will show results from the dark energy survey, and I will name some students and postdocs at Penn and others. The outline of my talk is I'll introduce these three puzzles in cosmology. Then I'll introduce how we use gravitational lensing to measure the growth of structure. Then I'll address this question of how, just very general question, how do you extract information from maps? Whether they are pictures of cities, whether they are X-ray of your body, whether they are cosmic surveys, what is all the information in a map? And how do we get it? And that'll bring me to some concluding points on deep learning. How many people know about this? 2 days ago, this is not cosmology. There was an object that was identified, which is not from the solar system. You remember Oumuamua? Then there was another one some years ago. Then another one 2 days ago. Pretty exciting. It's from the galactic plane. All right, the first cosmic puzzle you may have heard about that according to some data, the universe is expanding faster than we expect. What does it mean than we expect? That means that we have measurements from the cosmic microwave background from when the universe was 400,000 years old. If you take those measurements and you say that our universe has cold dark matter and dark energy in the form of vacuum energy, then I can go from 400,000 to 14 billion, and the expansion rate should be 67 kilometers per second per megaparsec. And it's measured to be 10% faster. That's the simple version of the story. So the local measurements show a faster expansion than the standard model. So either there's some problem in the data or the standard model isn't quite working. Now you immediately notice something odd, which is that when you allow for dark energy, then the most extreme form of dark energy is vacuum energy, lambda. If dark energy is anything else, a simple scalar field that's evolving, then it's less extreme in the sense that its repulsion is weaker. So to get a faster expansion rate than lambda CDM, there's no way to do it in a simple model. So it means something even more crazy, that that the true model of the universe is much more complicated. For example, dark matter decayed into dark energy or something like that. So people debate whether this issue is real. Some people think it's a problem with the Cepheids and supernovae measurements. But if it is real, then the theoretical implications are pretty severe. Okay, I have two slides of cosmology equations. The first equation is the Hubble expansion rate. So it's very simple. The expansion, the square of the expansion is proportional to sum of the energy densities. The second equation is the acceleration equation, which in relativity, density and pressure both cause gravitational effects, and they show up in this with this factor of 3. And so we measure the left-hand side to be positive, which means that there's a minus sign, and so the term in the brackets must have another minus sign, so that you get a positive acceleration. So that is very odd, because for an attractive force like gravity, you generally expect negative acceleration, that it's slowing down. The only way, but it's possible in relativity to get rho plus 3p to be negative, if you have something like vacuum energy that has negative pressure. And in the simplest form, P is exactly minus rho, so W is -1, and that's called vacuum energy lambda. For anything else, W is bigger than -1. It's close to 0 for matter. It's 1/3 for radiation. For some dynamical dark energy, so dark energy is roughly speaking defined as W between -1/3, which is the critical value in that equation, and -1. So dark energy is in that range if it's sensible. Notice we set C to 1 usually. Any questions? Okay, so that was the homogeneous universe, how it's expanding, assuming a single value of the density and pressure. Our real universe is highly clustered. So we measure these things called 2-point correlations. And that's the definition, but I'll describe them more as we go. The second cosmic puzzle was in the headlines 2-3 months ago, and also 1 year ago. But 2-3 months ago, it was confirmed that dark energy is evolving in time. So this is the second empirical evidence that lambda is not the right description. What's even crazier is that at higher redshift, at redshift above 1, these data require W to be below -1. And I just try to explain why it's impossible with a single scalar field to get W to be below -1. So if this is true, then what we call the dark sector, dark matter and dark energy, are more complicated, almost certainly. It means that dark matter and dark energy interact with each other. Or dark matter is actually many things. And we think we say the whole thing is one cold dark matter, but in fact, there's some part of it is decaying, or it's interacting. So it means something like that. Again, there's a huge debate about this result. You can see there's baryon acoustic oscillation, supernovae, CMB. Everybody familiar with CMB, cosmic microwave background? CMB, and possibly recleansing. So you need all of these to get this result. So it's a little dangerous if you don't understand one data or the systematics of one data set, couple somehow go in the same direction as systematics from another data set. But right now, it's like a 3 sigma result. Formally, in the paper, they have a 4.2 sigma, but if you're interested, I can discuss with you why I think it's barely 3 sigma in real, if you think about it sensibly. All right. So this is evolving dark energy, and the phantom crossing is this fact that it goes from, I have a plot on it. Right, so this result is so important and new that it's worth understanding. So this refers to the fact that the early plasma was oscillating, and so even in the present day universe, this is an exaggerated version of these baryonic acoustic oscillations that were imprinted. And so we can pick it up in the distribution of galaxies and quasars and stuff. So this is a plot from the earlier paper that shows that when you plot the correlation function of galaxies, it has this peak where the size of the rings is imprinted. So this peak is measured quite well, and that tells you the distance at that time, and you can combine it with supernovae, blah, blah, blah. So it's a complicated story. I'm not going to try to explain. But when you're done, you get an estimate of W as a function of redshift. So you can see the error bars are big. These are 2 sigma error bars. But the best fit model is this green band. And at redshift 0.5, it has this phantom crossing, which nobody dreamed that we would need to plot this below -1, because the whole discussion was, is it -1 or above -1? As you can see, at high redshift, the error bars are pretty big. At the lowest redshift, they're smaller, but there seems to be a phantom crossing. And in this particular way of describing dark energy, this 2-parameter description, lambda CDM is 0, -1. And you can see, depending on how you combine the data, you have a 2 to 4 sigma result. Okay, so it's, I mean, if you read the paper, it's pretty convincing. Then you have to look really closely at the data to see that there may be some issues. Third cosmic puzzle, the growth of large-scale structure in the universe seems to be slower than expected at late times, roughly speaking, below redshift 1. The parameter describing the amplitude of fluctuations is called sigma 8 or S8. So this is called the S8 tension. And the funny thing is, this growth is slower, roughly speaking, where dark energy dominates. So again, it points to dark energy being something different. Questions? Okay. And again, this tension is, by some measures, the weakest statistically. So there's a lot to be discussed about how real these tensions are, but they are driving a lot of research, and this is the reason that the new surveys like Euclid are going to produce very exciting results either way. So this is a visual presentation of the S8 tension. So imagine this was the prediction from theory. You've probably all seen these n-body simulations of large-scale structure. And this is what we measure from data. So the measured universe is less clustered than the predicted universe. So we did like some kind of model independent reconstruction of the power spectrum. And at wave numbers of 0.1 or 1 megaparsec, we find this deficit. So the visual pictures were capturing this deficit relative to to lambda CDM. Okay, this slide is for the cosmologists, that there are really no successful theoretical ideas to explain either the first or the second tension. And if you take the first tension and the third tension, all the theories just kind of break down or they become extremely fine-tuned. So if you want to see a very simple model that accommodates the data for the SA tension, you can look at this paper that I wrote with Mengshang Lin, which shows that if you take the growth of structure and let it be steady from high redshift up to redshift 1 or so, and then around redshift 1, you make a transition, and it goes quite a bit lower, 20% lower, then that is the slowdown in growth of structure we need to explain the data. And we came up with this model because CMB lensing, which is the lensing of the CMB, which is at redshift 1000, it's lensed by everything between. And galaxy lensing, which is shown by the orange kernel. So these are galaxies at redshift 1, lensed by everything in front. They show slightly different results. So we were trying to accommodate both those results with this simple, it's actually just a 1-parameter model. So now theorists are actually using this simple model to match their real complicated theories to this. So it's a nice intermediary between measurements and theory. All right. Now I'm going to tell you a little bit about gravitational lensing. Not the beautiful, exciting stuff some of you work on, but weak lensing, which is the story of how these unlensed galaxies are distorted. I think you've heard about this before. This is a highly exaggerated version. The reality is that it's much weaker. So the reality is that we have to work with galaxies that look like this, in which the lensing signal is a tiny perturbation to the shape of the galaxy. And we detect it by measuring these 2-point correlations. So you take the shape on one side, think of a vector on this side, a vector on this side, and you dot product them. So if they're randomly oriented and you average over many pairs, you'll get 0 because the dot product goes from -1 to 1, the cosine. But if they're correlated, the coherent signal, then it'll give you a non-zero result. And so that's what we call the 2-point correlation function. It's stronger when they're closer, weaker when they're further apart. So it falls as you look at larger distances. So this is a large-scale structure field, a simulated field, and it shows a galaxy cluster in the middle, voids, all that stuff. And the shear pattern shows the direction of elongation. So from observations, we get a very noisy version of this field. And with the dark energy survey, we make these mass maps. So this is the largest galaxy mass map that Niall Jeffrey, Marco Gatti, and others made. And so you can see some of the biggest superclusters ever found in red and cosmic voids in blue. But other than that, it's just some stochastic field because we think the universe had some quantum fluctuation type things which grew with gravity. And so they still look like random fluctuations, but they are not exactly Gaussian. Due to nonlinear growth, the dark reds are darker than the dark blues because galaxy clusters become very dense. So given this map, you know, like it's pixelized. So this one has like 1 million pixels. Do we really need 1 million numbers to describe this map? Some cosmologists will say, no, you need 5, because my theory is described by 5 parameters, and that's the only interesting thing in this map. So roughly speaking, that's how people do cosmology. They extract 5 to 10 numbers out of this, and they say that do these numbers match lambda CDM or something more complicated? And do the values fit other data? So like the SA tension is the fact that one of those numbers, the amplitude of fluctuations that we measure from this map, doesn't quite match what the CMB would have expected, would have led us to expect. So I'll return to this information content later. So, sorry, this is kind of a complicated plot, but let's just look at this panel, or okay, maybe this panel. So this is angular separation from 1 to 100 arc minutes. So that's 2 degrees here. And this is the 2-point correlation of lensing shapes. And so you can see the axis goes from 10 to the minus 7 to 10 to the minus 5. So the typical value is 10 to the minus 6. So that is a 2-point function. So it's the square of a distortion. So the distortion is 0.1%, 10 to the minus 3. So that means if a galaxy was perfectly round, it would become an ellipse with axis ratio 1 to 0.999. So it's a tiny signal. And these different panels show galaxies at different distances. So this is called lensing tomography. So just like you can take a picture of your body from many different angles and make a 3D picture, we get some approximate 3D picture of the universe statistically. Okay. So once we have this measurement, we compare it to a model that has these 6 or 10 numbers, the density of dark matter, baryons, dark energy, neutrinos, the shape and amplitude of the power spectrum, and the expansion rate. So then there's all these uncertainties. There's another 30 odd numbers. And so in this big, that's why it's called high dimensional parameter estimation. We use Bayesian statistics and answer some basic questions. So I will show you results where we do something completely different called SBI, simulation-based inference, where rather than take measurements and fit a model to them and estimate parameters that way, we do something different, which is called simulation-based inference, in the sense that you put everything in a simulation. So you generate thousands or millions of these predicted maps and compare them to the data sort of directly without estimating covariance matrices. So it's a scary and powerful alternative way of testing theories, which is becoming necessary because the standard way of doing things is just computationally almost impossible. So I'll talk about simulation-based inference in a few minutes. This is a basic result that we have. Omega matter, mass density, amplitude of fluctuations. The value doesn't mean anything there. The value here does mean something. It says 30% of the energy density is in matter. And these are 68 and 95% confidence intervals. The orange are the predictions based on CMB plus the standard model of cosmology, lambda CDM. And you can see there's this mild tension. The CMB likes predict higher amplitude of fluctuations. So this is called the S8 tension. But can we make these green contours 2 times smaller?
Yeah, CMB plant 2018 that is in both plots, but in the one is the orange.
Yes. You know, these are 2 different papers. They're always different assumptions. So here, as far as I recall, they fixed neutrino mass, and that lets the CMB be more constrained. If you free up neutrino mass, then you have to, there's more freedom in the power spectrum at smaller scales, so it weakens the constraints. That's one of the differences. There may be others. Yeah, good point. So yeah, since you mentioned the plot on the right, so this is, as you can see, a couple of years old. There are quite a few newer results, but this shows the 3 lensing surveys: Subaru HSC, Dark Energy Survey, and KIDS, which you may have heard more about. And they all are lower than the CMB from Planck. But KIDS recently published a reanalysis in which their results change. So, all right. So now I want to talk a little bit about methodology. And I will introduce the idea of getting at the other half of that information. So 2-point correlations are just one thing you can measure. You can also measure 3-point, 4-point, 5-point correlations. You can measure the PDF, a probability distribution of the hotspots. You can do wavelet-based statistics, clusters, voids. These are all very powerful methods of doing cosmology. Or you can say, I'm going to do what's called field level inference, where I'm going to describe that, where you use the whole map. And the Euclid collaboration, since we are friends, I can talk about Euclid, published sort of, in one sense, a great paper. They had like, I don't know, 12 or 14 different statistics. And there was no guidance. You know, there's a team in the Netherlands, there's a team in Italy, there's a team in Spain. I don't know, I'm just making fun. Everybody had their own favorite statistic, and they all put it all together. And so it's a really nice paper. But we need some guidance. Nobody wants to show 14 different results. So we have actually, there's a paper that may be out in a month or so, where we've figured out a way to select 3 or 4 statistics that will get you more than 90% of the information. And then you don't need the rest. So it's politically, maybe troubling, but we cannot be using a dozen different statistics. And the other thing about that paper is that it's so complicated to implement that they did no tomography in that paper. And so, tomography is quite an important part of that. Yes. So yeah, an alternative is to just pick 1 or 2 statistics, but do them fully with systematics and tomography. Anyway, this is kind of a random.
You mentioned it's based on statistic results based on different methods. The 14 results are all of them different.
Yes.
Okay.
Yes.
Different.
Voids, peaks, topological statistics, point function, real space, Fourier space. It's great, actually. Yeah, you can.
Choose one.
Yeah. I mean, generally speaking, these are pretty complicated things. They may not even agree with each other. So when you have a dozen things, then, 12 choose 2 pairs of possible disagreements. It will take so many years to figure out what the hell's happening. No, but this is just one in a step of progress, I'm just making fun anyway. So there's a lot of challenges. Getting accurate theoretical predictions is really hard. Simulations are quite reliable for weak lensing because we are using pretty large scales. So it's just gravitational simulations. So one point of view is that, don't worry, make many simulated maps, and the measurement of the simulations is your predictions. Give up on analytical approaches, halo model, perturbation theory. It's so hard to make them accurate. That's one point of view. So theory predictions can be solved with enough simulations. There are many other systematics that I will not talk about, but I've listed the 4 leading ones in my opinion. And then there's the question of how to interpret and understand results, which I think is a general serious problem in cosmology. You know, clusters are nice. They're kind of, you can hope to interpret them. But I showed you just this 2-point function, right? It had so many panels. It's becoming very hard to get an intuitive understanding of measurements. People do a lot of tests of the measurements, but it's really hard to use common sense, physical intuition, things that are super important to do a sanity check. All right. I'm gonna show you results from just 2 of my favorite higher order statistics. One is just a 3-point function that I won't have time to talk about. But my joke about the 3-point function is that I wrote these papers, and then they were really nice theory papers, ray tracing simulations, analytical model, and then it took 20 years to make the first measurement. But I'm still pretty excited about it. So we have these 3 3-point papers, a methodology paper, and then 2 data papers on dark energy survey and Subaru that should be out within a month. They're both in internal review, and we get like a factor of 2 improvement in these parameter constraints. So for example, so you can see the S8 omega matter. The red is the combination of 2 and 3-point, and the area enclosed is half that of the green. It's funny, you know, usually when you apply things to data, it's always worse than in your simulation. In this case, we found the gain to be actually even bigger from the measurements. Just statistical fluctuation, a little bit bigger. Please look for our paper next month, but this is the simple version of this factor of 2. All right, now I want to talk about like more ambitious and kind of exciting things. This is a wavelet approach. So, you know, wavelets, so it's like you take some kernel like this. So it's like Gaussian in the middle, but it has a more complicated shape, and you smooth your field with that. There's one immediately appealing thing about wavelets. There are many different shapes, but there's one immediately appealing thing, that they're compact in both real space and Fourier space. Okay, usually cosmologists like to do Fourier transform, but you know, like a Fourier wave. So if it's in real space, it's like a wave, so it's infinite, and in real space, in Fourier space, it's a delta function. So there's this problem that something that is compact in one space is fully spread out in the other space. So wavelets have kernels that are compact in both. And they're a little more complicated, like they look like compensated filters. And they have a lot of power. So these authors showed that you can take all these phenomena, cosmology, sun, ocean, microscopic Ising model, and then with just like 20 numbers or so, you can recreate those top panels in some stochastic way. So, you know, the patterns look different, but the nature of the field, it's not exact, but you can roughly get. If you try to do this with a Fourier transform, imagine trying to do this with a Fourier transform. You will need like 10,000 terms. So here with less than 100 terms, you can capture all these information, a little bit sharp edges, you know, stuff like that. So especially useful for cosmology because you can also separate scales. So that's the original lensing map. And these are 3 different scales that are used, that are then combined to recreate it. And it shows how nicely the structures are separated. So Marco Gatti was a postdoc at Penn. Now he's at Chicago. He took this brave new step of doing a wavelet decomposition of those lensing maps and then inferring these cosmological parameters, S8 omega matter you can look at. And so he already got this close to a factor of 2. He used what's called simulation-based inference. So there was no estimation of uncertainty. That's why it's crazy. What you do is you just generate a family of simulations. You want to span a range of cosmological models. You want galaxies to have shape noise. You want photometric redshift uncertainties. You want intrinsic alignments. So you just take, instead of 1 map, you generate 1 million, which span, in which each physical variable is drawn from a distribution. And so if there's, a peak value of the redshift, most of the maps will have that redshift, but some of them will sample the redshift distribution. And then you use machine learning methods like dimensionality reduction, posterior estimation to get these nice contours. So it's much faster than sampling a high-dimensional parameter space with traditional methods. Estimating covariance matrices alone, like in Euclid, order half the effort's going to go in estimating and validating covariance matrices. It's so difficult. So it bypasses that, but it has its own dangers. The validation is super important. And there's always this risk with machine learning that what if the real universe is out of distribution? That your training data doesn't fairly sample the real universe. Then you may never find out that you're getting the wrong answer. Even using traditional methods, that's a real problem, but at least there's a hope that you'll see some signature. So this is the sense in which I said this is cosmology is in flux. Traditional methods are almost hitting the barrier that they cannot handle the complexity of data and theory. And the new methods are pretty new, and so the dangers are not fully understood. I say that even though I totally believe our result, because I think we've done all the validation.
In this plot, you compare with cosmic shears or second order statistics. If you do
Yes.
higher order, you also have a gain with this.
Yes, I have not yet written a paper with more than 1 higher order statistic at a time. Yeah.
No, okay, but yeah, so simulation-based inference with respect to 2 point plus 3 point.
Yeah.
It's also in that case, you have a gain with respect to, so if you compare SBI with not just second order, but second order plus third order.
So that's what this is. So this is second order, and this is second. Oh, sorry, this is second order. This is second plus third.
Okay.
Okay.
So the second order is okay. Is the cosmic shear.
Yes.
The other one is the third.
Sorry, second order plus wavelets.
Second order plus wavelength. Okay.
Yes. And the paper that we'll put out in which we do second order plus third order, it's not SVI. Yep.
I have one curiosity. The only thing that scares me to start SBI method, because I'm interested since a long time. But the thing that scares me is how long does it take to prepare your data sets? Because
You mean the simulated
yeah.
data?
So the running the analysis is very fast.
Yes.
But to run the analysis, you need to prepare the data sets.
Yes.
For example, Marco, when was in UPenn, how long did it take to build the data sets? 2 years, 1 year.
This is a difficult question to answer because Marco is slightly superhuman. So any answer I give you will not be directly applicable to, other people. He did it in, I think, less than 6 months.
And that related question, this depends, I imagine, on the dimension of what you're seeing, the requirements that you. So the computational requirements, so are still where there is a gain on the computational power that you need. If you think about that, you maybe need bigger decisions. I don't know.
Right, so the way this works is first you make theory maps. And then you add systematics. So like suppose I have one full sky map, then I generate 100 more in which the photo Z's are slightly wrong. And then for each of those, I generate 100 more that have different levels of intrinsic alignment. So they multiply like that. All right. Now for what's called field level inference with deep learning. So I'm almost out of time, but this stuff is, so I've saved the visually easy part for the last. You've heard about ChatGPT, and you've hopefully heard about diffusion models. They are both magical in different ways. Diffusion models learn how to go from a real image to pure noise. And they do it in 1,000 steps. So you add a little bit of noise, a little bit of noise. And then there's this amazing result from discrete math that you can reverse the process. So you can recreate, having learned all those 1,000 steps, you can go from pure noise to a cat or a dog. And you can do it again and again and generate new images. So that's how, you generate images. So Supranta, a postdoc, and Michael Jacob, a second-year undergrad student, 19 years old. They're like equal. These days, high school students, first year, second year students with machine learning, they are amazing. So they did this really nice work where the top panel is 3 different redshifts, dark matter maps. And the bottom panel shows how the model starts from noise and tries to recreate that map. And so you'll see slowly, it starts to converge on something quite close to that structure. So we've used deep learning to generate realistic maps. And then I'll show you how you use deep learning to do all of cosmology. And so there are 2 architectures for images, convolutional neural nets and transformers. And I personally believe that every scientist should learn about these 2 architectures because they're probably coming to your research, if not today, then next year, but they're also affecting all of humanity because ChatGPT works with transformers. So, so what is field level inference? Or even kind of SBI is doing the following thing. This is data. This is one simulation. That one doesn't look right. This one, between the first and third, it's pretty hard to tell which is the right one, right? So this is the exercise. I've given you a map. Tell me which theory is the closest match. And so deep learning does this in this kind of brute force way. And along the way, for science, the challenge compared to the rest of society is that we want to estimate posteriors. So we want to get uncertainties, not just classification. I think I should skip this. So this is a one-slide introduction to convolutional neural nets. The crazy thing about deep learning is that we are going from fitting a model with 10 or 100 parameters to now, in order to estimate those 10 parameters, we are using a deep learning architecture which has millions of free parameters. You know, just as ChatGPT has trillion free parameters. But it works. And so at the end of the day, you can say my data looks like this one. And so this is an early demonstration by the Zurich group. You can see the truth by the star is off, so it wasn't working perfectly then. But since then, there's a DES paper. And then my student Kunhao, first year graduate student, he wrote this paper in which he said, well, let's start from scratch. For cosmology, what would be a good CNN? And he built one that was 100 times smaller than what everybody else uses and actually performed quite a bit better. In particular, there's this problem with overfitting. If your training data is not huge, then you learn some weird features. And so he showed that his smaller model had much less overfitting. The training and validation loss functions agree, unlike the previous models, where during training you get a great loss, but when you test it, it's actually much worse. This is the other paper that I recommend. We try to introduce transformers to astronomers, but it's really meant for anybody. And we have this frequently asked question. For example, when you type something to ChatGPT and it generates the first word of its answer, has it really done 1 trillion calculations to get that word? Yes. Like, it's a huge model. And that's why it might, accelerate global warming. So anyway, it gives you, since we are physicists, it's kind of amazing. You can understand all the math in 2 pages. So we get that math. Okay, I think I'm mostly done. So these are my philosophical thoughts on machine learning. So of course, in cosmology, it's kind of everywhere already. If you if you think of machine learning more broadly, and it's speeding up things, it's improving things. Neural nets are often both accurate and fast. Whether it's going to do the big job of comparing theory to data directly in the way that I showed is an open question. What is true is that for image analysis, convolutional neural nets and vision transformers are the methods of choice. And so you don't have to look at a dozen things, For time domain data, transformers, if you have a big enough training data, transformers are the best. One really important thing for astronomy is multimodal deep learning. The first step in deep learning is that you take a word, you take a pixel, you take a number, and you represent it as a vector. And when you train these models, these vectors move around. And then things that should be near each other, like words in a sentence, end up near each other. So once you understand this first step of embedding vectors, then you can see why multimodal deep learning, which is kind of a crazy thing, that words and images can talk to each other. Why that is natural, and for astronomy, where we have spectra and time domain data and images and stuff, why that's potentially really powerful. Like with LSST, we're going to have time series data, So for like variable stars or supernovae, rather than thinking of it as a 1D time series, you can think of it as a sequence of images, which is what it really is, and just use these methods to get that information. Interpretability is the biggest problem in using machine learning for cosmology. It's the biggest problem in AI for humanity. So there's a huge amount of work. I have a paper with a computer scientist. The other people on the paper are a psychologist who's analyzing text and a surgeon who's analyzing MRIs for surgery. And so this computer scientist is trying to help all these different applications with interpretability. In our case, it is when you learn S8, which parts of the image contributed the most? But it's a completely unsolved problem. People are making small steps. All right. That's my final slide. Cosmology has shown has got 3 puzzles: the expansion rate puzzle, the structure formation puzzle, and the evolving dark energy puzzle. If the data are correct, then they point to new physics. Theorists are in very early stages. How we'll access all the data is a big part of progress. And I showed you some initial steps. Thank you.
Questions?
So diffusion models like Midjourney, for instance, has problems in reproducing the number of fingers of humans, which is a very important feature in humans. And so I was wondering if in cosmology, like there is this risk of producing images, but maybe they are missing some very important feature that then makes problems.
Yes. The real answer is that we are not actually using them for cosmology.
Okay.
We are using them for, like suppose you're using a CNN for cosmology. Then what we do is we use a diffusion model to do a first step of training, because the diffusion model can generate many maps fast. And then the model is already pretty close to the right one. Then we do a final training with real simulations. And that really improves both the speed and accuracy of our results. So we are not yet susceptible to the danger of 7 fingers. Yes. Good question.
Other question. So what is your feeling about if those methods, like machine learning based methods like ChatGPT that you show, if they're able to extrapolate in the parameter space beyond your expectations, for example? So do you think there is room to iterate with these tools and extrapolate and give you some interesting answers?
I'll give you one interpretation of your question. You can ask ChatGPT to write a science fiction story and say that write me a story about some creatures on this moon of Jupiter, and the creatures should be able to move in triangles, and they live on trees upside down, blah, blah. And it'll write you a great story. There's nothing like it in its training data. So when people say that AI is stupid, it's just reproducing, summarizing what's in the training data, that's not actually true. It's quite creative. It can write new songs. It can write new songs. So if your question is, can it figure out that this data requires, to just pick an earlier example, dark matter, 10% of dark matter decaying into radiation, even though that was not in my simulations? Probably not. Because it can write new poems and new science fiction because it has seen a billion poems. So it's doing some kind of interpolation, even though it's a totally new creative output. Our training data is too small for it to be creative, in my opinion. Yeah.
We didn't comment because we promote something. So it seems that every year there is something new in this kind of structures, CNN, deep learning. Finally, it's ChatGPT. Now, do you think that, I mean, if we, for instance, learn the architecture of ChatGPT, then at least for 10 years we are done, or still every year we have to?
I mean, the funny thing is there is a constant change and progress, but there's also stability. Like CNNs were invented in the 80s or 90s.
Yeah.
And they are still one of the top two bands. The most dramatic new thing is a transformer, the attention mechanism, 2017. So yes, that was a dramatic shift in time, in sequential data.
Now you suggest to study this transformer.
So if you ask computer scientists this, they don't really. But at least right now, there are millions of people investing in transformers, but within transformers, there are some significant variations. Like there's something called swing transformer that we are finding works better for cosmology because CNNs have some symmetries that transformers don't. And we like symmetries. So the swing transformer puts in some symmetries, stuff like that. So yes, one has to keep up with computer science literature. I asked my computer science colleague, how do you keep up? He said, well, there's only about 100 papers every day that are relevant for me. And they have huge groups. I have 10 students, so we each read 10 papers a day. Like by read, I don't know what. So they have it all, so they have like a plan for how to keep up, but they have to keep up. It's insane.
General question. If this should astronomer and astrophysics study those things in the details, or should we have computer scientists, engineers in our astrophysics group to do that? Like, because this is something that I think about like very much. What is my future? Like, I should be a computer science, and then after 1 year of studying computer science, apply it to my results, or should we do something else with our books?
It's a tough question. That's a very tough question. If I was starting from scratch, I would say that every science student should probably do 1 year of machine learning. My colleague Masao Sako and I, we started a 2-semester sequence. So roughly speaking, 4 months because these are hard courses. 2-semester sequence for advanced undergraduates called machine learning and the natural sciences. But it begins with Gaussian and Poisson probability distribution. So it's like statistics and ends with transformers. So if anybody's interested, I can send you the syllabus. You'll get an idea of what I think is a good training. But I myself barely know the stuff. I mean, professors are so far behind with machine learning that it's so hard to give a good answer. But it's certainly true that it's possible to learn it on the side. I mean, the online material is amazing. It's amazing. Like if you want to learn about, build your own neural net, build your own transformer, in 1 week, you can learn so much. Because you can also get the code, play with it. Like it takes a little while to find the right fit for you, but there are great resources.
Just a curiosity, in new physics that you were talking about, which is kind of a possibility, it's in the early stages or it's also tested with the
That's a good question. So people are doing simulations like Carlo showed me simulations of modified gravity and testing it with voids. So there's some new simulations of new physics, but like this new result about the evolving dark energy and the phantom crossing, there's almost nothing. Yeah, because it's such a surprising result. And a real physics model would have to be very complicated and it'll take time to build. And it's almost certainly wrong because when you make things more complicated, the possibilities are hundreds. So, but one of the tasks for new data is that we have to generate at least 5 different models which fit the new data in order to prepare our methods. Otherwise, we are preparing for lambda CDM or WCDM, and that is not going to be enough if the real answer is evolving dark energy.
Last question. So Bhuvnesh is also meeting as a meeting at 2:30 in the third floor, no, second floor of INAS. I reserved a room, so we can also chat with him later. There is another short question.
I just wanted to say one thing that, I have given you the machine learning AI point of view. If any of you are interested in knowing more, I am quite involved with AI at my university, outside astronomy and physics also. So I'm happy to talk about it. But of course, there is a way of doing cosmology that is almost no serious machine, which is still perfectly good.
Thank you so much.
Thank you.
Fascinating. Well, I want to tell you a story about machine learning and wine, because so we enjoy lots, drinking some glass of wine in the last days, and doing. So I was attending a meeting in Munich some years ago, some weeks ago, and a guy that was studying machine learning asked those machine learning algorithms to show a picture of friends drinking a glass of full wine. So he showed 4 guys, 2 guys and 2 girls, drinking a glass of wine, and it was a normal glass of wine. But the guy again asked, "But can you make it full?" And he was slowly making a little bit more wine. And again. So the guy had to ask many times to fill the glass full of wine. So this means that you need to interact a lot with those machine learning methods. So at the end, I think after 10, 20 iterations, the picture was 4 guys, 2 girls and 2 guys with a glass full of wine. So things that have never been seen in the data set. So I was extrapolating this image.
I mean, yeah, this is very interesting because ChatGPT and co don't have a world model. They have no idea how language works, no idea how physics works. So some very logically very simple things are extremely hard for them.
Thank you, Book. Thank you.
Writing text, right? Writing text on is very difficult. The images, painting some text on the image.
Oh, yes.
That's
That can sometimes be real tough. Yeah.
So I think it was about 8 years ago.